Okay, so the question I want to talk about today is whether or not in ERM ERM a, a approximation of a function based on some model is going to be a good one. So let me explain what I mean by an ERM. Okay, so assume that I have like space of possible function that I want to use for my learning. So these are functions from the domain of data and labeling to there are functions from a domain of data to my labeling. Okay, erase that. So, and the function comes from this space here. Okay, so there's a space of possible functions, and I want to pick one of them. And the way I'm going to do it, I'm going to get like a set of examples. This is the set of examples I'm going to get. And I'm going to go over all of these functions that I have here and pick up the function that is best suited for this one. So maybe, I'll look at the sum of the indicator of whether f of xi is different from yi. Okay, I'll just count how many times they are different, and I'll pick up f that is the best one. Okay, so I'll pick up the best function, the function that is the smallest function in H that does that. Okay. I'm picking up this set of data from the data is coming from x times y using some probability measure on it. Just picking up randomly using the probability measure that applies. I'm picking endpoints, and then I see which function in H is the best function according that does the minimum possible mistakes on these endpoints, and that's the function I'm going to pick up. Say, okay, this is my function. This is the function I'm going to use. Okay. Now, this is something we're doing all the time in machine learning, right? So maybe can someone give me an example of an H you are using in machine learning with standard algorithms?
Uh, is H going to be like a set of classifiers, right?
Right. So can you give me an example of
So like I don't know. Well, so F is one of the class F in here is could be one of the classifiers. So like maybe uh, H could be I don't know. All a bunch of different H could be random forests with different settings or something. Or not sorry, not random.
yeah,
Yeah, yeah,
exactly,
yeah. And then
exactly,
F could be one of the random forest or settings.
exactly. This is exactly it. Or for instance, you have a neural network, and H is all the possible neural network if you take into account the weight. And then you pick up one neural network, that's your F. And F star is the neural network that you pick that is the best one on the points, x1 to xn, x1, y1 to xn, yn. So it could be anything that you're using for learning will have that. I'm not interested in how you currently. I'm not interested in how you search over H, but I'm saying you pick one of them. It's the if it's the best one on the points that you've seen, is it going to be a good one? That's the question I'm trying to ask. Okay, makes sense up to now? So the answer is very interesting. Actually, the answer is an adversary can pick up a piece so that it can fool you completely. And let me explain that. So let me open a new one. In for this one ERM. So what I'm going to give you now is an example of how an adversary can pick up a point, pick up a distribution function so that ERM is going to be completely fooled. Now, to do that, I need to first remind us about something about probabilities. So with probability, you have the notion of a density function. So a density function, like for instance, for the normal distribution, density function looks something like that, right? So this is some function. A density function is some function. We call it G because I used F before. So that the integral between minus infinity to infinity of the function is equal 1. And basically the way to get the probability, so the density function is something that can give you the probability. And now if you want to know the probability of some event, like what's the probability of getting a number that is less than some x, You just need to integrate between minus infinity to x. Okay, so that's how you get the probability. Okay, so what's the probability of the random variable being less than x? It's just the integral between -0 and x of the density. So that's one of the ways to express probabilities with densities. Now, what is the, assume you have a density, what's the probability of a random variable with a density having a specific value, say 0? What's the probability of that?
Zero.
0. So the probability of any event any one, sorry, not event is the wrong term. Any point, probability of any point is just 0. And the event is also, you can say event. I don't want to go into that. But basically, the probability of 1 point. What about the probability of 2 points? So what's the probability of x equals 0 or x equals 1? What's the probability of that?
0.
0. Now, what's the probability? What's the probability of x equal 0 or x equal 1 or x equal k and so on ad infinity? What's the probability of that?
Still 0.
Still 0. Okay, so the interesting thing is that we see here is that the probability of any finite set of points, or for that also countable number of points, is just 0. You're working with density. Okay. Now this is true in general. It's also true. So it's true with in any case in which we are working with density. So assume that I'm going back to the ERM thing. Assume that my set of function is a function that is has some specific values on certain points and 0 otherwise. So any function f which has 1 on a finite set of points. Okay. So think about f as something like that. So it will say, for instance, at this point it gives me a 1. This point it gives me a 1. At this point it gives me a 1. Finite, and everything else is 0. Okay. That's my h. and assume that the adversary chose some density function. So what's the probability? Now I'm choosing my training set. I'm choosing x1, y1, xm, ym. This is my training set, okay? Now, x1 is a point, and y1, x1 is a point in that I chose according to the probability G. And yi is just either 1 or 0, right? Because then I choose some function here. I fix some function, like I fix a function f, I meaning I'm the adversary. So the adversary is trying to make me completely confused on my data set. And the adversary knows that I'm using ERM. So I choose any function in, and then choose a density function, and randomly choose endpoints. So what's the probability is that yi here, so the way I determine yi is I calculate f of xi, and it's equal yi. So because f is coming from h, so if xi is one of the finite points in which f is 1, then yi is going to be 1. Otherwise, it's going to be 0. Correct? So there's going to be only finite number of points in the sample for which f of xi is going to be 1. Because f is defined as 1 only on a finite set of points. Okay, so what's the probability that I'll have a 1 here in one of the data samples? What's the probability that I'll have a 1 on the first data sample? Meaning I choose x1 randomly using G. I calculate f. F is one of the functions here that has 1 on a finite set of points. And I set it to the value of f. So what's the probability that the first sample is going to have a 1 as y1?
I'm guessing it's still 0 because you have to choose one of the finite numbers
Yes.
that map to 1.
Yeah, and in fact, that's true for all of the endpoints. So the probability overall of having a 1 here is 0. Right? So it means that I'm going to get x1 0, xm 0. So did I learn anything about f?
No.
No, I don't know anything about f. I didn't learn anything about f because f is, f is just, I learned something about f when I see a specific point in which f is 1. Otherwise, because I know that f is of the form, ones on a finite set of points. So I need to know which points are 1. Now, if I get points in which f is 0, I didn't learn anything about f. So you see that an adversary can completely fool an approach here that is using what they call ERM. Okay. So ERM, in this case, can be completely full. Still, ERM is one of the major learning paradigms that kind of match a lot of the things that we do at some level. So I thought it was interesting to show you how sensitive ERM is to, to the assumptions of what can be chosen in terms of the probability distribution. Any additional questions or comments on this? Okay, so thank you very much for joining, and continue next time.